Focus of today's session is to revisit logic gates. Now, if you studied computer science at IGCSE, you would know the common logic gates that we encounter are NOT, AND, OR, NAND, NOR, and XOR, also known as EOR, exclusive OR gates. We should be able to identify them, construct the truth table for each of these logic gates, construct a logic circuit based on these gates, and these logic circuits can be created from a problem statement, another logic circuit, for example, to simplify it, or a truth table, which then needs to be converted back into a logic circuit. Or you can change it from one form to the other. So, for example, a problem statement to a truth table to a logic circuit and vice versa. Let's go back in history for a bit. Let's start in the early 1800s. So you had Charles Babbage and his analytical engine, which used gears. We jump a bit forward to the late 19th century, and then you had census machines which used bells, switches and relays to do computation. Then World War II happened, and we had valves and vacuum tubes which were used in the quite famous machine of the time called Colossus, which helped the UK break the German code, and that led to a quick resolution of World War II. Now these devices were using manual mechanisms to enter program and data into a computer, and that was often quite tedious and quite slow, especially the human side of things. Now fast forward to 1947, so a team at Bell Labs in New Jersey, US, led by William Shockley, was trying to build an improved amplifier. Now this is a fundamental electronic circuit used in radio, radar, telephone equipment and all sorts of things. So amplifiers used at that particular time were very temperamental. They had temperamental valves, and Shockley believed that he could exploit perhaps the quantum mechanics of electrons to build something called a solid state amplifier. So he ended up gluing contacts of gold leaf to the tip of a germanium crystal and attached another contact to the base, and Shockley's team was able to control the current flowing between the gold contacts just by turning on and off the voltage that goes through it. Now, when they added a small voltage at the base, that caused electrons to fill the gap in the crystal, allowing for a much larger voltage to flow between the contacts. Shockley demonstrated this device, and it was called a lot of names, and one of the names was a transfer register, which eventually became transfer resistor, because the device transferred resistance from the base to the flow circuit, and then eventually the name transistor came about. 9 years later, Shockley and the engineers John Bardeen and Walter Brattain were awarded the Nobel Prize for their invention, which has just changed the way the world works. So as transistors came on the scene, everybody wanted to build the first transistor computer, and Tom Kilburn at Manchester University in 1953 led the way with the first transistor computer, but it still used a number of valves. That basically meant that Bell Labs' own Tradic computer in 1954 was the first fully transistorized computer. And then IBM came on the scene and all sorts of other companies, and eventually things grew and grew and grew. And even though amplification may have driven the transistor's invention, but computer scientists quickly realized its importance as a very fast switch. So now, if you look at the development of computers and the processing power from the humble beginnings in 1947-48 to where we are now, we have crossed boundaries, we put people in space, we can create other virtual worlds, entertainment, games, you name it. All of this is only possible through the humble transistor and eventually the even humbler logic gate. Now let's look at what exactly is a transistor. Now we already talked about that it's basically a fast switch, and computers store and process binary numbers which are represented in computers as electrical signals. So a high voltage represents 1, whereas a low voltage normally represents 0. And in practice, modern circuits work on around 5 volts. So anything over 3 volts is counted as on, while anything below 1.5 volts means off. So the transistor allows the 5-volt signal to be turned on and off electronically at lightning speed without the need for mechanical relays or those temperamental valves. A transistor normally takes 2 inputs and produces an output. Specifically, it takes data input that arrives at the collector and a control input at the base, and if the base input is 1, then 1 will flow to the emitter. And why is this particularly useful in computers? Well, think about arithmetic and logic operations. Representing true or 1 as a high voltage and false or 0 as a low voltage, these transistors can be combined to make logic gates, and those logic gates can be arranged to perform arithmetic. So let's start as usual by looking at the key terms. You need to be familiar with logic gates, what they are, electronic circuits. You need to be familiar with the term logic circuit, which is a combination of logic gates that's designed to carry out a particular task. Truth tables are basically methods of checking the output from logic gates. They're all possible binary input combinations, and based on that you generate an output. You also need to be aware of Boolean algebra, a form of algebra linked to logic circuits which are based on true and false, and then what logic notation is all about, a method of representing a logic circuit in written form. The picture on your screen is George Boole, who basically framed Boolean algebra. Now, George Boole was so obsessed with mathematics that he actually taught himself French so he could read a book called Differential and Integral Calculus in its original language. And by the age of 16, he was teaching mathematics in a local school, and by 19, he'd opened his own school in his hometown of Lincoln. And in 1854, he published a book called An Investigation of the Laws of Thought, which showed for the first time the manipulation of symbols in equations can be used reliably for logical deduction, and even introduced mathematical probability to the world. But we're interested in logic gates, so let's look at logic gates in a bit more depth. Logic gates are electronic circuits in computers. Often you will find them in memories, often things like SSDs and controlling devices, and they're made out of thousands if not millions of these logic gates. So logic gates basically take a binary input and then they produce a binary output. Several logic gates combined together can form a logic circuit, and these circuits are designed to carry out specific functions. To check the output from a logic gate or logic circuit, we normally use something called a truth table. Now at IGCSE level, you should be familiar with the following logic gates: NOT, AND, OR, NAND, NOR, and exclusive OR. The symbols are on screen, so do pause the video and just get yourself familiar with these. Now, chances are that you already know about these logic gates, so a task for you would be to draw the logic gate simple, hopefully by not rewinding the video and having a look, but just from memory. And maybe you might also want to try drawing out the resulting truth table for each one. For example, the NOT one is pretty straightforward. You put in a 1, you get a 0. It's the opposite. You send in a 0 as an input, you get 1 as the output. So you draw a table and then you jot these input and output combinations out. So have a go at this task and we'll see how many of these you got right, or if you have forgotten about some of these, then that's okay as well. So let's start by looking at the NOT gate. The description is basically the output X is 1 if the input A is not 1. Now we can write it in Boolean algebra as X is equal to A, and we put this little line on top, which means that it is the inverse of A. So if A was 1, A with the line on top is 0. We can also write it as X is equal to not A, which is something you should be familiar again from IGCSE levels, which is logic notation. So we write that in words, not A, which basically means 0, not 1. A is always 1. Now you will notice that in Boolean algebra there are 3 new symbols. A dot represents the AND operation, a plus sign represents the OR operation, and a dash above a letter, for example A with a dash on top, represents NOT. So that's the new bit of information that you'll probably see for AS level. So just get yourself familiar with that. Apart from that, the symbol should be pretty straightforward. Hopefully you made it, and the truth table should look like the one that's on the right hand side of the screen. The AND gate, again, the output X is 1 if input A is 1 and input B is 1. So basically if you get two 1s, you get a 1, otherwise everything else is 0. Now you can write this in logic notation as X is equal to A and B, and is capital. And if you're using Boolean algebra, you simply say X is equal to A dot B. The dot denotes AND. Now hopefully you got the symbol right. Hopefully you got the truth table right. If you forget these symbols, the best way to remember them is to create some kind of analogy or link. So I always think the D in AND, that is basically what the gate is. So they kind of look similar. So pretty straightforward to remember that. You can try something similar like that. So if you're forgetting an exclusive OR symbol, you can think of something like maybe a starship or a Star Trek communication badge with an extra line, a visual image, and connect it to that. Now an OR gate, again, hopefully you got the symbol right, you got the truth table right. The output X is 1 if input A is 1 or input B is 1. So any 1 gets you a 1, otherwise it's 0. And you can write that in logic notation as X is equal to A or B, capital OR. And in Boolean algebra, it's X is equal to A plus B, plus being the symbol for O. So again, pretty straightforward. Next up is the NAND gate. Now NAND is a combination of NOT and AND. You can denote it by drawing the AND gate and putting a little circle at the front of it, which indicates NOT. Hopefully you got the symbol right. Hopefully the truth table is right. It's basically the inverse of AND. So the output X is 1 if input A is not 1 or input B is not 1. Okay, so as long as both of them are not 1, you output a 1. If both A and B are 1, you output a 0. Now you can write this as X is equal to A NAND B, NAND in capitals, in logic notation. In Boolean algebra form, you simply say X is equal to A dot B, which is A and B, and you draw a big line over the top of it which indicates not. So that becomes not A dot B. Okay. Next up is the NOR gate, which basically is an OR gate with the little circle drawn at the front of it, the opposite of OR. Hopefully you got the symbol right. Hopefully you got the truth table right as well. If you haven't, just pause the video and have a look. The description basically is that the output X is 1 if input A is not 1 and input B is not 1. So if you got a 1 at either A or B, you can't output a 1. So the only time a 1 is possible in a NOR gate is when both inputs are 0. Now you can write this in logic notation as simply X is equal to A NOR B, NOR is capital. And in Boolean algebra form, you simply say X is equal to A plus B, which is OR, and you draw a big line at the top, which is the NOT part. So it's not A or B, which is basically what NOR is. Now the final gate is XOR or exclusive OR. This is a special version of an OR gate, which basically looks for exclusive 1 inputs. Hopefully again you got the symbol right and you got the truth table correct. The description basically is that the output X is 1 if input A is 1 and input B is not 1, or input A is not 1 and input B is 1. So basically the 1 has to be exclusive in A or B. Now you can write this down as X is equal to A XOR B in logic notation form, XOR being capital, and X is equal to A dot B not plus, which is OR, A not and B. So it's quite complicated because you are trying to represent every logic condition that's possible in an XOR gate. Now there are different versions of writing this. You could also write it as A or B and A and B not. There is an entire field called Boolean identities, which you'll probably encounter in year 13, where you can use that to resolve complex logic circuits, simplify them, and that's something we'll look forward to studying in year 13. But for now, all you need to know is that an XOR gate is represented in Boolean algebra by one of those two notations. So pick the one that makes sense to you. Okay, let's try creating a truth table for a logic circuit. So hopefully this is pretty straightforward. Again, if you know this from IGCSE, this will be easy peasy. If you've forgotten about this, then you might want to just recap. So in this logic circuit, there's a number of gates. There are 3 inputs, and different inputs go to different gates. What you normally do is divide the circuit into different parts and try to resolve each part separately. So A and B, when they go into the AND gate, you take that output and call it P. B and C, when they go into that NOR gate, you call that output Q. P and Q then go into an OR gate, you call that output R. And then in the final exclusive OR gate, C and R go into that, and you call that output X. So you need to resolve each gate separately, and then that leads you to the final output of X. So try that, and hopefully you get the right truth table. Another example is a word example. So sometimes you get a question like this. A safety system uses 3 inputs to a logic circuit. An alarm X sounds, so this is the output, if input A represents on, so that basically means A is 1. And input B represents off, so that means that B is 0. You can do that by just putting in a NOT gate. Or if input B represents on and input C represents off, so C should have a NOT gate after it to turn with a 1 into 0. You always start with assuming A, B, C's are 1. Now you've got to produce a logic circuit and a truth table to show the conditions which cause the output X to be 1. So you start by writing the logic notation first. You can also write the Boolean algebra form if that kind of helps you out, and then based on that you can then create your logic circuit. Now on screen is an actual exam question, which is a bit more complicated. You've got a table that outlines different conditions. You've got some context at the top. You've got some conditions at the bottom. You will need to convert this into a logic notation or a Boolean algebra form, and then you need to design the logic circuit based on that, and then eventually work out the truth table. So do pause the video, do rewind, go back to the first one, the diagram version of the logic circuit, make the truth table for that, then do the 2 word examples, and do share your answers with me. Okay, so why do we actually use these logic circuits? Well, electronics companies need to consider the cost of their components, because the more complex we make these components, the more expensive the device is. You need to come up with new manufacturing techniques, which are normally called fabrication techniques, and there are obviously time constraints as well, because you need to release products in the real world, because your profit margins depend on it. So when you're designing and building logic circuits, you are considering efficiency and the use of the same type of logic gates, because you can then buy them in bulk and use economies of scale to drive costs down. Now the ways electronic companies review logic circuit designs include things like using off-the-shelf logic units and building up logic circuits as a number of building blocks. So we don't actually work with the individual logic circuits anymore, or the individual logic gates anymore. We build blocks like half adders, full adders, or even more complex than that, 8-bit transistors, 16-bit chips, and so forth. Now, if you're custom designing one of these type of building blocks, then it makes sense to simplify the logic circuit as far as possible, to reduce the space, because the more logic gates you use, the bigger the chip gets. And this can have an impact in design when you're creating something like the Mars rover or satellites and so forth. And even kind of like designing mobile phones. We want smaller phones, thinner screens, so you need to reduce the amount of logic gates that you have, the transistors and the components you use. Now one common building block is the NAND gate. So it's possible to build up any logic circuit using a NAND gate, and therefore logic circuits are often simplified by just using NAND gates. NOR gates are also used, and think back to when we were talking about EEPROM technology, electronically erasable programmable read-only memory, NOR gates were used there. So NAND gates are cheaper, used in SSDs, and NOR can also be used, but a bit more faster, so these are used in EEPROM chips. Now NAND gates, why are they a common building block? That's because they have a greater output threshold, they use a lot less space and have smaller delays, so they are preferred rather than the more expensive NOR chips. However, NOR is also very quick, probably much more quicker than NAND. However, there's a spacing issue there. Now, your task is to look at these circuits, 3 of those, designed by NAND gates, create the truth table and compare them to your original ones, and then let me know which circuit belongs to which original gate. Like, is there a NOT gate here? Is there an AND gate here? Is there an exclusive OR here? So work that out. So work out the truth tables for these circuits and then compare it to your original gates, and then see which ones of those gates are represented by these NAND circuits. And that will kind of give you a hint. In the exam, you'll get questions like this, where you will need to simplify a logic circuit using NAND gates. So do pause the video and go to this task. Your next task is to draw the logic circuits and complete the truth tables for these logic statements and Boolean algebra statements. So this is a bit of practice. Pause the video, go through these, and of course do share these with me. You've got a couple of exam questions which are on screen, so you can test your knowledge on these as well. Okay, the next set of questions are all about the previous topics. So we looked at RAM and ROM. We looked at how printing works. So these questions are related to that. Make sure you go through these as well, just to review what you know. And the final set of questions are all about OLED, microprocessors and control systems, ROM and RAM, and 3D printers. So it's an ideal opportunity for you to review what we've covered so far. But coming back to today's session, hopefully you know what logic gates are used for. You are able to identify common logic gates. You're able to construct truth tables for these logic gates. And you can resolve logic circuits from both expressions, logic notation based ones, and Boolean algebra based ones as well. And finally, you should be able to redesign existing logic circuits using NAND gates. That's all for today. I will catch up with you in the next lesson.